sediment. From here on out, the water's not as clear.
Walk us through the first strata we're looking at here.
What we call concretion. Okay, so this is where the cement is different from out here, and it's been a chemical reaction around the perimeter there. You see it grades out into this sandstone around it. So it's a chemical reaction within the sandstone to form these concretions. We also know that there was quite a bit of movement of water, because down here you can see on this rock face malachite, green malachite, copper carbonate. Okay, so this is how we know that there's trace copper in some of these rock units. See the malachite here, copper carbonate. And it's probably come out of some of these finer bands. See the malachite here? It actually precipitated around a little pebble in there. So again, a difference in chemistry with whatever was in solution, including the copper, and of course the carbonate, so there has to be some lime in the water to precipitate, and copper to produce malachite, copper carbonate.
I don't think I've been back here when this stream is flowing all the way down.
Yeah, I have before.
I think one time we came up and it was raining up here, and it started a little stream. I remember that because I got that on video. But I mean, yeah, it's maybe the first time I've seen it flowing up here.
It's the first time I've seen it flowing all the way down, but I have seen it flowing up here. Have a look up as you come up. You're seeing up above you.
Whoa. Yeah, right?
Heather,
Okay, gotcha.
look up.
A little famous picture there.
That was.
What's that?
I don't know.
Stone. And I'm going to talk about the dating of the Tapeat Sandstone tonight, so we don't have to go there. But the Tapeat Sandstone, of course, we walked up and we went through the Great Unconformity, which we saw from the boats this morning. Okay? We went up through the Great Unconformity. We're now in the first of the flood rocks, flood layers. This has been dated at 508 million years. That's the official age for the Tapeat Sandstone now, 508 million years. And I'll tell you tonight how that was derived. So we've got the Tapeat Sandstone here, okay, and then you've got all the other layers above that. Look back downstream and we go all the way up to the Kaibab limestone at the top. Roughly 4,000 feet of layers. Now, if you look through this opening here, you'll see there's a different rock type. And when you go over to the shade, you might have looked up and seen the north rim with the snow on it. The Kaibab limestone at the north rim is 3,000 feet higher, approximately, than the Kaibab over there. What's happened is we're at the edge of the plateau here. Okay, the plateau to the west was pushed up, and the reason it was pushed up where Joe is, just past the shade, is the Butte Fault, B-U-T-T-E. It's a fault that was pre-flood. It was in the crystalline basement rocks, and because of what was happening at the base of the Earth's crust here in Western North America, because of what was happening, and I'll explain again later in the trip, but the Pacific ocean floor was being pushed underneath, and instead of going down steeply, it went flat, and it lifted up this whole area. And what happened is that the weaknesses were these faults in the Precambrian, these pre-flood faults, and so the Butte Fault got pushed up there by several thousand feet. And these layers were draped over it in a bend like this, okay? A bend like this. We call it a monocline, okay? And if you do Highway 89 from Marble Canyon Lodge up to Jacobs Lake, you actually climb up the monocline where the layers are bent. We came out from Las Vegas, we came over the North Rim, and then we went down towards Marble Canyon. The plane followed the monocline, this bend, okay? In this instance here, you can see the results of the bending. And then eventually, the movement was so great that the rock was sheared off. But what you notice is that the bending here is quite smooth. Remember what I said about on the first night? If you've got man-made concrete, something that's rock hard, then when you try to bend it, it's going to shatter. And here's the problem, because remember we've got 4,000 feet of other layers above, and then you've got the grand staircase, much of which was in place. The folding occurred about 50 to 70 million years ago. So there's a gap of about 450 million years between the laying down of the Tapeat Sandstone and the bending of the rock. with all the other layers on top, it was under considerable pressure. And so the secularists say, well, with heat and pressure, the heat of burial and the pressure of burial, the grains will move past one another and the layers will slide past one another, and it will bend smoothly over millions of years. And that's in the literature. But no one has really looked, because if there was sufficient heat and pressure, you'd expect textural, and also with the movement, you'd expect textural features that would be evident under the microscope. Whereas, from our perspective, if the sandstone was deposited, here's Johnny now. If the sandstone was deposited at the beginning of the flood, at the end of the flood, when the plateau was pushed up, these layers were only 12 months old. And so they were still moist because they'd been under the flood waters. So when the plateau was pushed up, the layers would bend smoothly. And furthermore, we would expect that then the layers were cemented. In other words, it was deposition, bending, and then cementation, hardening. Whereas the secularists say it was deposition, hardening, and then bending. Now, if it was deposition, then bending and cementation, the rock should be the same as Tapete sandstone samples from miles away. We came through 60 Mile Rapid this morning. On a river left, there's a beach. We collected one of our samples there, because what we want to do is I wanted to compare samples from in the hinge zone, that's the bend, from out in the limb, away from the fold, and then miles away. Because if it being deposition, then bending, and then cementation, it should be the same no matter where you collect a sample. Whereas if it was deposition, cementation, and then bending, the bending would have affected the cement here. It would have broken the cement and it would have affected the textures, whereas it would be different miles away. It would be still the pristine, okay? And nobody had taken samples, nobody had tested it by looking under a microscope to see if these features were there. And so that was the objective of the study, to take the samples in this fold. There's 4 folds, and you're going to see all 4 of them. Most people don't get to see this one because they usually just sail by down the river. The 7-day trips don't usually get time to come up here. So, what happened? Well, I said on the first night, I went to review the literature, and the only photographs I could find of the Tapete sandstone under the microscope were taken in 1945, published in 1945, and were black and white. Nobody had done the basic research. So I used optical microscopy. In other words, you get the sample, you cut with a diamond saw a thin slice, you glue it to a microscope slide, and you grind it down till it's paper thin, 30 microns thick. We know that because it's the standard thickness. It's the point where quartz crystals go from yellow under the microscope to grey. And that's by definition. And we use a petrological microscope, which is different to a biological microscope. You've got a polarizer with a light source, so you get polarized light comes up through your sample, and you have a polarizer above this sample that you're looking through it. If the polarizers are like that, it's the same. They're parallel to one another. The light comes through and everything looks plain. But as soon as you cross the polars, what happens? The different minerals have different colours, and when you rotate the stage, they change colour, and you can identify which minerals. It's a well-known technique. Well, so I spent hours and hours and hours. Actually, COVID was a blessing because all my other events got cancelled. I had to work at home, so I took the microscope down to my basement and spent thousands of hours slide by slide by slide, taking photographs of every observation point, notes, etc. on all these samples. And then I had a friend who cut the thin sections at the lab in his lab in Calgary, Alberta. He did X-ray diffraction analysis, which is where you crush the rock and you put X-rays through it, and the X-ray pattern determines which minerals and the quantities in the rock. So he sent me those results, and I could compare it under the microscope to see that I was getting the estimates correct. He also did scanning electron microscopy, particularly looking at the cement. And so what did we find? Well, first of all, we found that there was no difference in the samples whether they came from the hinge, the limb, or from miles away. Absolutely no difference. The cement was still pristine. There was no evidence. In fact, in the paper, the first paper that's been published on this fold was published in February this year. I had to make sure that if I made a statement that something was in every sample, I had a photograph from every sample. So the paper got very large, but that's beside the point. Otherwise, I could be accused of cherry picking the data. But what I found is that you can still see the primary depositional minerals and the primary depositional features. Remember I mentioned the muscovite, the white mica? Well, in the sandstone in the distance, you see the muscovite flakes, and they're wrapped around the other grains because they're soft, and they get compressed and they're wrapped around, and sometimes they get broken ends and everything. Well, it's the same in the hinge, identical, everywhere. The feldspars were the same, and the cement was the same. It wasn't broken, it was pristine. And so, in other words, we were looking at the primary depositional features no matter where we took them. I also, what I did is I went to the literature and went to the textbooks about if this rock had been bent under temperature and pressure, what features would I expect to find under the microscope? So there's a whole section of the paper listing all the features and describing all the features, and then I go through my samples and show that none of those features are in them, that only the same features in the fold are the same in the samples miles and miles away from the fold. So the answer is deposition, bending, and then cementation. Deposition at the beginning of the flood, bending at the end of the flood, drying out after the flood. Not deposition, 450 million hardening, 450 million years later, bending. So and we know that these folds, you can trace them in other side canyons. You've got the folding goes all the way to the rims, up to the kaibab. And you can see that from the aerial views of the monocline. So that means the whole sequence was bent without fracturing, because the whole sequence had been deposited within the flood. So that automatically wipes out 500 million years of supposed geologic time. And so that's the significance of this research, and it's being duplicated at the moment with the other folds. The next paper is on the Monument Fold, which will pass tomorrow, late tomorrow. We'll point it out to you. It's right by the river. It's in the Tapete Sandstone. Later in the week, we'll go past the Mat Katameeba Fold, which is in the Muave. And at the helipad, there's the Whitmore Helipad Fold right there in the Bright Angel. And I'm working on those papers, the last two papers at the moment. So the next one is in review, and I expect to finalise that when I get back. So it's pretty interesting research. The other thing is, I think I told some of you heard a little bit of the story how I had to fight a lawsuit to get permission to come and get these samples, because I was opposed as a creationist by the academics who were the reviewers for the National Park Service. Alliance Defending Freedom got involved, Freedom of Information Search got the backstory, and when the park wouldn't budge, we put a lawsuit on them, and when the lawyers saw that we had all the documentation, they gave in. Well, Alliance Defending Freedoms knew that the Park Service could accuse us of malpractice when we collected the samples, so they sent a videographer with them. with us. And the videographer recorded everything we did. That footage was made available to the guy who produced the Is Genesis History movie. Early in 2017, that movie is released. If any of you haven't seen it, you should. Go online to Is Genesis History, type that in Google, and you'll get it was a series of interviews on location of various specialists, including myself. I was interviewed at SP Crater at Flagstaff, which I could see from the plane flying over, get into Las Vegas just last week, and down at Sedona. Steve Austin was interviewed at the South Rim. Doug Petrovich, the archaeologist, was interviewed. We're talking about the evidence that Genesis is history and why it has to be taken seriously. Well, we now produced a sequel to that. It's called Is Genesis History? Mountains After the Flood. And it'll be coming out this summer, and it'll be focused on this research project and implications of it. And so look out for that. It'll have some of the footage shot on location during the research trip, including us scrambling up there collecting samples. It'll have footage in the lab, interviews, photographs of the rocks under the microscope, etc. And so you can look forward to that. That's coming out this summer.
What are you doing? Chipping off like a section of rock, like to get the
All
sample?
we wanted was fist-sized samples.
Oh,
Okay. One of the academics that opposed us, and this is what they did with the Freedom of Information search, because they wanted to put certain strictures on our collections. They wanted me to go in and photograph all the collection sites first and then submit that to them for approval. And we knew that was further stonewalling. So we did a Freedom of Information search and we checked. One of those professors who was opposed to us getting fist-sized samples, that same year, the year before, he'd got a permit to collect football-sized samples and to have a helicopter take them out. So, it's not as if the Park Service wouldn't grant you permission for it. It was clearly well-viewed discrimination. And it was very important that it was be fought because other creationists have had their research applications rejected and they haven't taken up the fight. But now we've got a precedent. The interesting thing was that the lawsuit was filed 4 days after President Trump signed an executive order that the government bureaucracy couldn't discriminate based on worldview. So it was a slam dunk. Yes, sure.
It sounds like that video was a blessing, right?
Sorry?
They sent the videographer along with you.
Oh, yeah, the videographer was a blessing having him on, yes. And Answers in Genesis has got that footage as well. And Answers in Genesis is working on doing a series of programs of a trip through the Grand Canyon with all the teaching spots and also featuring the research. So that'll be coming as well.
But the videographer was the Alliance Defending Freedom, right?
Correct.
Yeah, see, that's a I'll call it a
And
friendly videographer.
The lawyer who was spearheaded it, Gary McCaleb, is now on the board of Canyon Ministries. We did have two soft premieres of the documentary back in end of February, beginning of March. One was at Cedarville University. Joe knows about that. To get feedback, and there's a lot of work, there's a lot of animations in it that had to be refined to illustrate it. It's also going to have Steve Austin talking about the carving of the Grand Canyon, the evidence for the lake systems behind the plateau that then down cut the canyon. So that'll be part, and there'll be an animation to show that, to replicate the carving of the Grand Canyon. So it'll be well worth waiting for and looking out for it. It'll be about 100 minutes long. The first documentary was about that long as well. So, why don't we can have questions over in the shade, because it's going to get hot here, but if you want to take photographs, by all means, at any time, but we can adjourn to...
All right, Andrew, so we're up here at the Carbon Fold. Why don't you tell everyone here what we have and what's the significance of it?
Yes, we're in the Carbon Canyon fold. It's the folding of the Peat sandstone layers. And you can see that the layers are bent smoothly. So the question is, was it the sandstone deposited, then was it bent while it was still soft, and then hardened? That would fit the flood because the sandstone would have been deposited early in the flood, the bending at the end of the flood when the valleys sank and the mountains rose, and then drying out after the flood. That makes sense. The simpler view is that the sandstone is 500 million years old, the bending took place 450 million years later. By then it would have been so hard that it should have shattered. And so our research has shown that the flood model best explains the bending of these layers, that it was deposition at the beginning of the flood, it was bending while the sediments were still soft from being filled with water still, and then hardening as the waters dried out after the flood. Peat sandstone behind us here, okay, and above us you've got the Grand Canyon sequence, which you can see over in the distance there. In between, in this valley here, we've got the rock unit that's above the Nankoweap. Remember when we left the river, we were on the Nankoweap formation, and the Great Unconformity was the Nankoweap. Well, there's two other rock units between the Nankoweap and the Peats in other parts of the canyon, and this is one of those locations. This is called the Galeras Formation, and the other unit is called the Quagont Formation. The Quagont Formation is the one that has a lot of stromatolites in it, and this one here, you can see these bands we're standing on here. They're very iron-rich bands, and you can see some of these layers are tilted. They're tilted as they were bent near the fold, whereas out there they're more flat-lying. These are probably pre-flood ocean floor sediments. The reason I say that is because the Quagont has those stromatolites, which were the pre-flood reef environment. And so we feel that these are pre-flood ocean floor sediments because they're very fine grained. You can see they're different colours. In places you'll see there's a lot of carbon in the rock. So again, people have raised the question, and we may as well talk about it here. You know, fossils in the pre-flood world, or even fossils produced of microbes in the end of the creation week before the fall. Well, they don't have a nephesh. It's animal life that was judged by God at the fall. Plants were given for food prior to the fall. So a plant doesn't die the same as an animal that sheds blood. That's why Cain's sacrifice was unacceptable, whereas Abel's was, because his was a blood sacrifice. And so there's no problem in seeing microbes in some of these fossilised microbes in some of these rocks. Stromatolites, remember, they were the algal mats, and you'll see evidence of stromatolitic units or beds in this Galeras. We'll see some on the way down. If you see some of these harder units with hard little ripples in them, they're the fossilised algal mats. They're stromatolitic limestone units, thin bands in the Galeras Formation. So they're right through this sequence. So we think they were pre-flood ocean floor sediments. They may have probably after the end of the creation week, when there was still a lot of sedimentation of stuff coming off the continents. We can't be sure, but this is where these fit in. Now, if you look back over here, you'll see the Peat sandstone, and then it disappears up the fault line, goes up through that notch up there, where you follow that cliff line, the Butte Fault. And that fault can be traced for miles, for quite a few miles.
How do you trace it in this area between here and that notch?
Well, you're looking along the line of the edge of the Tapete Sandstone there,
Okay.
following where you get a change of rock type, and you can see it better from the air. It's been mapped in aerial photography. The full extent of it that's exposed is over 300 miles.
Wow.
Now, if you go to look this way, you can see that the fault line goes through that notch there, and then you've got a different rock unit on the right here. In fact, there's another fault that branches. You can see the Tapete Sandstone comes along, and then there's a valley, and then you've got a little bit of a notch, and then you've got that black rock. There's another fault line that goes through there. That fault line is called the Palisades Fault. It's a branch of the Butte Fault, and it crosses the river where we meet the rafts. And we'll be able to look across the river and see where the Nankoot Formation has been bent into the Palisades Fault on that side of the river. Black rock is the Cardenas basalt. There's probably 10 lava flows that are stacked. We can sample them here. I say we sampled them. Steve Austin and I were working on the Cardenas basalt back in the 90s, and we sampled up in Basalt Canyon, which we'll pass either tonight, this afternoon, or tomorrow, where you can go in and see more of these lava flows. You get a good view of them from the Desert View Tower, watchtower. When you look down, you can see these lava flows. And so there's a branch fault in here. So we're going to actually hike down this drainage channel, keep on hiking down this drainage, but where it drops into the Lava Chua drainage, there's a waterfall, a dry waterfall. So near the end where this tributary is supposed to go into the Lava Chua Creek, we've got to do a slight climb over a ridge and down to get around the fall. The waterfall, the dry waterfall. So that'll be the last challenge of the trip. But it's a defined trail, not clambering, and it's just a steep gradient as you go down there. And then we walk down the drainage of the Lava Chua Creek down to our raft. You'll see below, and I'm mentioning this now because we'll probably get strung out as we get going. Below the basalt, the Cardenas basalt, you'll find the Docks Formation, which is a red-brown, 7,000 feet thick, monotonous sequence of siltstones primarily. Yeah, so that's what we'll see. And where the boats are parked, you'll see the lava above you on the hill above, and looking downstream, you'll see the docks. Across the river, we could talk about that, but you'll see where there's been movement on the Palisades Fault, and these lavas have been pushed up. So that's what we're seeing around here. It was a dynamic situation. These fault lines were in place before the flood, but they were reactivated at the time of the end of the flood, when the earth started to readjust, and part of that readjustment was the pushing up of this plateau. And these were the weak points. These fault lines were the weak points where the earth's crust moved. And these flood layers, of course, were still soft, and that's why they bent easily. As I said, you can replicate the eventual breaking off in a lab experiment where you've got soft sand layers, and you move the floor of the tank and start to bend the layers, and they'll eventually shear off after a while and produce a breaking off like that. So it all fits. It all fits.
Andrew, are we looking at the edges of an upturned ring?
Yeah, well, this is the layers here are flat out there, but they've been bent as they come near the fault. So they're affected by the fault as well.
And this is what?
This is the Galeros Formation, which is below the Great Unconformity. Okay, well, we'll head back to Joe and
So we're at Upper Tanner Camp
Upper
at mile
Tanner.
69? Okay.
That peak up there is called Comanche Point. That peak. That cliff line back over there is called the Palisades of the Desert. There's the Desert View Tower. Easternmost overlook at the eastern part of the South Rim. And this is the turn into the Grand Canyon. We're turning from north-south to east-west here. So if the canyon opens up and we'll get more sunshine, or wind, or sun, we'll get the sun earlier and the sun later, generally. And the plan was to be above the Granite Gorge for when the water rose, because the water, once it rises, it'll be a very fast trip through the inner gorge, and there'll be no campsites in there. Often we can camp a little bit further and then run into the gorge and camp in the gorge, but most of the camps in the gorge will be flooded. So the idea is tomorrow we'll do 50 miles. Big day. We'll do 50 miles. We'll stop a couple of miles down, a quick stop to see some archaeological stuff. Then we'll go down to Hance Rapids and they'll scout the Hance Rapids, which is the first technical 10. And then we'll go down to Phantom Ranch, only to stop at the beach to get water, not to go to the ranch itself. There's a spigot. We pull in, we go under the Kaibab suspension bridge, pull up at a beach called Boat Beach, and 100 yards from the beach there's a spigot. And we'll take the empty water jugs, fill them up with water, put them back on the boat and take off again. Then we'll head on down and try and find a spot for lunch. And the idea is to get well down. We'll get the second technical 10 as Crystal. They'll definitely scout that. There's a saying on the river with the boatman, ABC, alive below Crystal. He's been known to flip more boats than any other rapid. So they'll be looking at it. They'll be looking at it very carefully. And the idea is that's about mile 100, just above mile 100. The idea is to get down to about mile 119, 120 tomorrow night, which will set us up beautifully for the rest of the trip. We will pass at mile 116 something the Monument Fold, which is another fold in the Tapete Sandstone, and we'll point that out to you as we go by. And that's the second of the folds that I've been working on. The paper is currently under review. I expect to get all the reviewers' comments back by the time when I get home back from this trip, and then we'll get ready for publication next month. So, what I wanted to talk about first up is again to review where we're at in the rocks, and so we can look up there and we can see the Tapete Sandstone, and underneath it we can see the Cardenas basalt. Okay, you can see the Cardenas basalt back over behind us, and we're down in the docks. So we're well down in here now. The docks is 7,000 feet of monotonous siltstones primarily. And we'll see a little bit more of the Cardenas basalt around the corner. There's a canyon around us called the Salt Canyon. And so we're going to go through the docks, and then very quickly we'll go through the Shinamou, Hakatai and Bass. And the rapids and the Hance Rapids will be there at the Bass Limestone, and we'll see first of the silts. Where the silt magma got squeezed like toothpaste. And I'll point that out. The silt is intruded into the Bass Limestone, and the heat of the silt cooked the limestone and produced asbestos, and hence hence mined asbestos there, long fibre asbestos, which is used for fabric. They use this long fibre asbestos for theatre curtains.
Oh, wow.
When you had the lamps for lighting. Okay, so we'll point that out. You'll see that, and we go then we go immediately into the gorge very, very quickly, and suddenly we'll lose most of these rocks, and you'll only see the Tapete sandstone used most of the time, and the great unconformity. Now, as I said before, basalt. Let me preface it with this remark. If you were to take all the rocks on the continents and mix them and grind them up, and then chemically analyse them, the composition would be about that of a granite. Okay? Not all the rocks are granite. I'm just saying if you took all the rock types, mix them all up and analyse it, you get about a granite. Basalt, okay, so the earth, the crust, the continental crust is made up of that composition. So if you were to melt crustal rocks, you get granites. That's what happens. You take a rock like the Docks, and under heat and pressure, it'll eventually melt. And when it recrystallises, you'll produce something like a granite. So basalts can't come from the crust. Basalts come from the mantle below. Okay, the mantle below. And that's very important to remember. That there's a difference in composition, and we'll come back to that another night when we talk about the continents and the oceanic crust and things that happen during the flood. But the point I wanted to make is that when you get a rock like a siltstone and you start to heat it and under pressure, different minerals melt at different temperatures. Okay, just like you've got different metals will melt at different temperatures. And so the reverse is true. Different minerals will crystallise at different temperatures. And so that produces interesting effects with the rocks that result. So if you've got a siltstone that starts to metamorphose, what do we mean by that? Well, the quartz particles and the clay in the siltstone, the quartz won't melt, but the clay will. The clay will transform into minerals like muscovite, mica. It might even transform into a garnet. And so the resultant rock will be a quartz mica schist. And you're going to see some of those rocks in the inner gorge. You're going to see garnets even in some in some places I've seen things like tourmalines as well as garnets. A whole variety of minerals that are produced by the transformation under heat and pressure. Now, if the rock really gets heated up, then the first of the minerals that might melt will be quartz and feldspar. They melt at lower temperatures. And so what can happen is, if the temperature and pressure stays at the level where quartz and feldspar melt, the pressure is going to cause the molten quartz and feldspar to migrate along fractures, okay? Because it's going to get squeezed. So it's going to find the path of least resistance, because now it's mobile because it's molten, and it's going to find its way into fractures until it finds it starts to cool down again. And so what you're going to see when you get in a gorge, you're going to see these quartz veins and pink and white veins and bands in the rock and that where the what we say the metamorphic rock has partially melted. Parts of it melted, partially melted, and it melted to produce quartz and feldspar. Now, so I said if it goes the whole way, then when it recrystallizes, it will produce a granite. And so we're going to go into the inner granite gorge, the upper granite gorge, which goes for most of from Hants Rapids, mile 78, all the way to mile 120, where we'll camp tomorrow night. We'll all be in inner granite gorge, and we'll find bodies of granite that intrude into the schists, and different bodies of granite. The bodies are called plutons, after Pluto, the god of the underworld. So granite is a plutonic rock, igneous rock. It cools under the ground. And each pluton or body of granite can be slightly different in composition, and it's given a different name. And so we'll get to Grapevine Rapid, and you've got the Grapevine Pluton or the Grapevine Granite. We'll get further down, and you've got the Zoroaster Granite by Zoroaster Creek. You get down to Bright Angel at Phantom Ranch, and you've got the Bright Angel Granite. You go below that, and you've got Pipe Creek Granite. You go below that, you've got Horn Creek Granite, and so on. There's different granite bodies in amongst these schists. And so I'm mentioning that now so that you get an idea for what you're going to see. The whole atmosphere of the canyon is going to change. Here it's broad and it's lots of sunshine and different colours, and suddenly you've got this narrow gorge with high walls, and the river goes from wall to wall, and it's dark, it's foreboding because of the darkness of the schists, and so you'll find it's totally different in atmosphere. By the way, I've seen bighorn sheep. You've got these steep cliffs. I've seen them clambering up those cliffs. They're amazingly sure-footed. Well, tomorrow we're also going to see at Monument Fold, near Monument Fold, the oldest dated rock in the Grand Canyon. The Earl's Chasm granodiorite is a type of granite. It's supposed to be 1.84 billion years old. And these Cardenas basalts, okay, they're supposed to be 1 billion years old. How did they get those dates? Well, of course, prior to the discovery of radioactivity, they had to use all sorts of other techniques to try and figure out how old the rocks might be. But then radioactivity came along, and suddenly they thought they had a process that they could use to date rocks. And so the idea is that, say, uranium, which was the first one to be discovered, if you know how long it takes for uranium to decay into lead, okay, you know how long it takes for uranium to decay into lead, and you can measure that in a laboratory today. I'll come back to that in a moment. And if you assume that there was only uranium in the rock when it formed, you can analyse the rock for how much lead is in the rock now and calculate back to when all that lead was originally uranium, and that's then basically the age of the rock. That's very roughly the technique. I'll come back to that and explain a little bit more in a moment. Well, let me use the analogy. An hourglass clock. You've got two glass bowls and you've got sand grains. You tip it up so all the sand grains are in the top glass bowl, and over the next hour the sand grains fall. Okay? And so, you're in the kitchen and you decide you want to bake a cake. So you get the ingredients and you put it in the pan, and you go to put it in the oven. You put it in the oven and you turn up your hourglass clock, okay, and you go out of the room. You go and do the laundry or something, and then you come back and you want to know how long it was since you put the cake in the oven. Well, what do? You look at your hourglass clock and you look at how many sand grains are down the bottom. And if half the sand grains are down the bottom, how long were you out of the room? 30 minutes. Because it's taken 30 minutes for half the hour's worth of sand grains to fall to the bottom. And so that's the analogy. When the sand grains are up in the top glass bowl, they're uranium atoms. When they fall, that's radioactive decay. And when they accumulate at the bottom, that's the daughter product called lead. So you have parent atom, uranium, a daughter atom, lead. And so that was traditionally the first method that was utilised. Until more and more problems accumulated and they abandoned that, and then they latched on to potassium that decays to argon. And that worked for a while, then they found certain problems and they went to other methods like rubidium decaying to strontium. And one of the more recent ones is samarium decays to neodymium. Now, you probably haven't heard of those. They're rare earth metals. But neodymium is particularly one of those critical metals that we are concerned that the Chinese have too much of and the rest of the world doesn't have enough of, because every one of those wind turbines, the magnet has neodymium in it, because it produces a better, stronger magnet for generating more electricity more efficiently. And even our cell phones have neodymium in them. So these are critical metals in the rocks. And so the technique is used where the geologist goes out and he collects his rock samples and he sends them to the laboratory. And the laboratory measures whatever he chooses, whether it's uranium and lead. The laboratory does the chemical analyses. And there's nothing wrong with the chemical analysis. I could send pieces of the same sample to 10 laboratories and I guarantee they'll get very similar chemical analytical results. Because the laboratories where they do this work, they spend millions of dollars building them and ultra clean processing rooms, etc., because they're looking for very minute quantities of these elements. But it's the interpretation of the chemical analysis that we dispute, because you see there's three major assumptions in this method, these methods, three major assumptions. First of all, you've got to assume that when the rock formed, it only had parent atoms in it, or you knew the initial conditions, what was in the rock when the rock formed. Well, how many geologists were there to see the Cardenas basalt form? None. We don't have an eyewitness who was there to test it, to know. So we have to assume what the original composition of the Cardenas basalt was, how much uranium had in it, or how much lead, etc., how much potassium, etc. Now, of course, with your hourglass clock, you were there and you knew how much was in the beginning. So you tipped it up and all of it was at the top and it fell. Well, that's well and good. So the second assumption is that there's been no contamination. Now, the Cardenas basalt has supposedly been sitting out here for 1 billion years. Have they been able to check through all those billions of years whether there's been any contamination? No. Most of the samples that are collected for dating rocks are collected at the surface. And every rock sample I've ever seen under the microscope is always weathered. You can see the effects of weathering. In fact, you can go down a mine shaft and go down up to a mile and you'll still see the effects of weathering. And so weathering is a real problem. Uranium, for example, is very easily leached from rocks, very mobile. Potassium can be leached by groundwaters as well. Remember I told you about the fossil log on the first day? how the uranium was leached from the Chinley Formation and then travelled through the Chinnerup conglomerate and then latched onto the carbon in the logs. See, uranium is mobile. See, you didn't realise it, but while you're out of the room, your mischievous 10-year-old lifted up the lid and put some more sand grains in the top. And you thought you'd been out of the room for 30 minutes, but in fact you've been out of the room for 40 minutes because your system was being contaminated. And then of course, you have to know the rate of decay. Well, it's all very well measuring it today, but have the geologists been around for millions of years to check that uranium has always decayed at the same rate? No. No, not at all. Not at all. You know, what would happen if your mischievous 10-year-old not only added more sand grains at the top, but also put a little bit of water in there to dampen the sand grains so they didn't fall at the same rate, they slowed down. So your hourglass clock is now absolutely useless because it can't read the time. So how do the geologists know? I mean, it's easy to measure the decay rate of uranium in the laboratory. You can get a pound of uranium and you can figure out, remember in your chemistry, you know, Avogadro's number, 1 mole, 6 times 10 to the 23 atoms. Okay, yeah. Taylor's nodding his head, he remembers. Okay, so you can work out how many uranium atoms are in your pound of uranium. Stick a Geiger counter against it for a year. Every click of the Geiger counter is a uranium atom decaying. At the end of the year, you know how many atoms decayed? You know how many you started with? Hey, presto. But the interesting thing is, the decay rates have only been measured for the last 100 or so years. And I embarked on a project to collect all the data from the original measurements that have been done to see if there'd been consistency. And no, there hasn't been consistency in the results. The only way they got consistency in the end is dating a rock by 2 methods, and if the 2 methods didn't agree, they changed the decay rate of one method to the other method to match the uranium date.
Say that again, please.
They took rock samples, for example, the Palisades rhyolite on the coast of Lake Superior, north of Duluth. They dated it with potassium argon and they dated it with uranium lead. The methods didn't agree. So what did they do? They said uranium will make that the standard and we'll change the decay rate in our calculations for potassium so that the end result will be that the two match. Okay? So that's what they did. So none of these assumptions are provable because the scientists weren't there to measure the rocks when they formed, to check for contamination through the millions of years, or also to check for the decay rates through the millions of years. So that's a real problem. And actually, none of those assumptions are reasonable because we know that when rocks form, they have uranium and lead in them, both. And I'll give you some examples of some of the problems in a moment. We know that these rocks can be easily contaminated by weathering. And so these methods are very problematic. So let me give you some examples. I did a study where I went to the 2 major textbooks used in universities around the world in geology classes to teach this methodology. And so I took examples that they quoted in their teaching programs. So this is not, I didn't make this up. This is from the literature, okay? And there are abundant examples in the conventional literature where the methods have failed and failed miserably. But they don't always highlight that. They always try to highlight where it works. And they often cherry pick the data that gives them the results they want. If they rarely date by more than one method, but if they date by more than one method and they don't agree, they cherry pick the one that fits what they wanted. And there's a paper coming out in July. The US Geological Survey has a database of dates, and very few have been done by more than one method. And the study shows that when it's done by more than one method, statistically, you find that the dates more than half the time don't agree with one another. So that's not a very good outcome. So let me give you some examples, some that you're familiar with. You all remember Mount St Helens when it erupted in May 1980. It blasted out the top 1,300 feet of the mountain, and there was a new crater. And inside the new crater, there was lavas continue to come up and build successively new lava domes. Sometimes they got blasted away, a new one kept forming until the volcanism started to die down. And in 1986, the last of these lava flows, October 1986, is there on the wall of the dome, of the lava dome. So Dr. Steve Austin hiked up in there and got a sample. He got a piece of the sample and he separated it into its constituent minerals. There's methodologies for doing that. And so he sent to the laboratory samples of the whole rock and each of the mineral components. And he got potassium. He didn't tell the lab where it came from. We knew how old the rock was because it was 1996 when he sent it to the lab. So the rock was only 10 years old. And it went to the lab, and the ages range from 350,000 years for the whole rock to 2.8 million years for pyroxene, one of the minerals, the dark minerals in the salt. The conclusion was that, of course, that the assumption that there was no argon in the rock to begin with is wrong. And that was already well known in the literature. Why? Because when a volcano erupts, some of the gases that come out of the volcano, most of what comes out of volcanoes is steam, right? But you get various other gases, and one of the gases is argon. And so argon that didn't come from radioactive decay of potassium in the rock was in the gases that were trapped in the gas bubbles in the lava and then included in the mineral. And so if you didn't know that, you wouldn't know that a lot of the argon didn't come from radioactive decay of potassium in the rock. Now this is well known. Our brother here, Scott and Sebastian, they come from the Big Island. If you fly and land at Kona, right by the airport there, in the golf course, is a lava flow that erupted in 1800 and 1801. And it gives potassium argon ages up to 43 million years by potassium argon. And so it's well known that, and there was papers in the 1960s where this was well documented in the literature. And it's a persistent problem. How do you know that all the argon you measure in your rock from potassium has come from all the argon you met has come from in situ radioactive decay of potassium since the rock formed. You don't know that. And I'll come back to that in a minute. Now it's also a known fact, it's been a problem for over 50 years in the literature. It's called the lead isotope paradox. Hawaii is what we call an ocean island. You've got the Canary Islands, you've got the Azores, you've got Easter Island, you've got Guadeloupe, you've got all these ocean islands. And they've all got recent lava flows on them, many of them have been observed to erupt. So we know the ages, the true ages of the lava flows. But they all give ages using uranium decaying to lead of between 1 and 2 billion years. And so in the literature, it's been called the lead isotope paradox, trying to figure out why. Well, the answer's here in the Grand Canyon, by the way, and it confirms the conclusions that they've come to. But let's talk about some of the research we decided to do in the Grand Canyon. We decided that since in the literature they didn't date a rock by more than one method, that we were going to do a study in the Grand Canyon, because it was a great place to collect samples and everybody knows these rocks. Let's select 4 rock units in the Grand Canyon, get samples, send them to the lab, and date them by all 4 major methods to see if the methods truly do agree. Because in the textbooks, the methods should agree. The methods should agree. It's like having a different hourglass clocks, different sized atoms that fall at different rates. But if you start them all at the same time and measure today, you should calculate the same time. Okay? And so the geologists, that's why they don't use more than one method, because they believe that any one method should give you the same result. Well, we collected samples of the Cardenas basalt. We also looked at the results that were in the literature. And potassium argon gave us an age of 500, well, we did multiple samples, okay? You can calculate an age from a single sample, it's called a model age. But if you calculate ages from multiple samples, it's called an isochron age. And it's more statistically valid. So we always collected multiple samples so that we could get a better statistical result. So the Cardenas, and we incorporated some of the data in the literature as well. The Cardenas basalt gave a potassium argon age of 516 million years. Well, you know that's wrong, because the great unconformity is supposed to be 542 million years old, and the Cardenas basalt was below the great unconformity. Well, that's a bit of a problem. Well, even more of a problem is that the rubidium strontium age is 1,111 million years. It's more than double the potassium argon age. And then the samarium neodymium age was 1,588 million years, 3 times the size of the potassium argon age. I mean, that's like trying to hit a dartboard blindfolded. Which is the correct age? 516 million years, 1,111 million years, or 1,588 million years? Or D, none of the above. And so that's a real problem. In fact, we went on to date a sill, not the sill at Hance Rapids, but a sill we'll see later tomorrow at Bass Rapids at mile 107. And it's a very interesting sill because remember I said different minerals crystallise at different temperatures? Well, because of that, the minerals have separated in the sill, so the sill has a different composition at the top to the bottom, which is ideal for radioisotope dating because you can get a better statistical spread in your analyses. Well, we got a potassium argon age of 541 million years, a rubidium strontium age of 1,050 million years, thereabouts, or 60 million years I should say. We got a uranium lead age of 1,250 million years, and a samarium neodymium age of 1,379 million years. Now notice something interesting. The potassium argon age was the youngest of both those rocks. And the rubidium was the next youngest. Okay? And then the uranium and the samarium were older. Now that's very interesting because we found a similar pattern. We dated the Else Chasm granodiorite and also tomorrow night we'll be camped amongst amphibolites, which are metamorphosed basalts. The Brahma schist in the metamorphic rocks is metamorphosed basalt, and I sampled those as well, and they gave a similar pattern of results. Now, when you see a pattern like that, what does it tell you? It tells you that there must be something systematically going on. First of all, potassium is the lightest of the elements. Rubidium is a little bit more heavier, atomic number wise. Samarium is a bit heavier atomic number wise, and uranium is the heaviest atomic number wise. Okay, and atomic weight. So potassium is potassium 40, that's atomic weight 40. Rubidium is atomic weight 87. Samarium is atomic weight 184. And uranium is atomic weight 238. And so the heavier the parent atom, the older the age. And furthermore, potassium and rubidium decay by beta decay, whereas samarium and uranium decay by alpha decay. Okay, different decay processes. And so the beta decays gave younger ages than the alpha decays. And so that means there had to be some systematic process that had occurred. And so the only way to reconcile the difference in the ages in the Cardenas basalt was to come to the conclusion that at some time in the past, decay rates had speeded up, such that the heavier the atom and the alpha decayers speeded up their decay more than the lighter potassium and the beta decayers. So imagine we had 3 hourglass clocks, potassium, rubidium and samarium for the Cardenas basalt. There's a real time period between the lava flowing out and crystallising and measuring today. That's the real time period. Well, in that real time period, the potassium argon clock ticked through 516 million years. In the same real time period, the rubidium strontium clock ticked through 1,111 million years. And in the same real time period since the rock formed till today, the samarium neodymium clock ticked through 1,508 million years. Okay? So if the decay rates weren't constant in the past, these methods can't be used to reliably date the rocks. And we found other evidence. We found 6 lines of evidence in total, 5 other lines of evidence that supported that conclusion, that decay rates had been speeded up in the past. You think about it, what catastrophic event occurred in the past where geological processes went off at catastrophic rates? During the flood. A byproduct of radioactive decay is heat, and heat is what drives geological processes, and we'll come to that again another night, what that implies. But it's likely possible that God changed the decay rates to actually start the flood event, and we'll come back to that on another night. But think about it, a rock that formed, say you had a lava flow in the first month of the flood, and higher up in the sequence you have a lava flow in the last month of the flood. The one in the first month of the flood would have decayed through 12 months of radioactive decay at catastrophic rates, whereas the lava flow at the end of the flood would have only ticked through 1 month of rapid decay. So you would expect the rock at the bottom to give you an older age than the rock at the top. In other words, the ages would be systematic as you go up through the record, and that's what we do find. That generally there is a systematic pattern, and that's the systematic pattern the secularists say, aha, you see, the methods work, and therefore the ages are absolute ages and correct. But you've got to remind them that, first of all, the decay rates haven't been accurately measured. They haven't been proven to be constant over millions of years. Contamination is a real problem. You have to assume the initial conditions, and you can show that argon can be inherited, lead can be inherited when the rock forms. In fact, let me give you an example that we're going to see. In fact, we're going to experience it. We're going to go over the last granddaddy rapid of them all, Lava Falls Rapid. Why is it called Lava Falls Rapid? Well, up on the rim, there's a volcano. I saw it from the plane flying out from Las Vegas. I could see it. Volkenstern. Here it is here. And it erupted after the Grand Canyon formed, and the lava spilled down the side of the canyon. So it was an incandescent lava flow, lava falls, and it was like an incandescent waterfall, but it was lava. And it blocked the Colorado River, and we'll talk more about that when we get down there. We'll be camping amongst these lava flows on our last night before we fly out in the helicopter. But more of that. Well, what are the ages of these rocks? These lavas in the western Grand Canyon. Now, there's evidence that some of the last eruptions, there's up to 180 volcanoes, they're on fault lines. Okay, so the lavas came up through weaknesses from the mantle below, up through cracks to erupt in these volcanoes. Some of the last of these lava flows the Native Americans may have seen, so they may be only several thousand years old. We get potassium argon ages of up to 1 million years. You get lead ages up to 2.5 billion years, or 2,500 million years. And guess what? The rubidium strontium age is 1,143 million years. The rubidium strontium age within this statistical era is exactly the same age as the rubidium strontium, as the Cardenas basalt. The Cardenas basalt gives a rubidium strontium age of 1,111 million years. That's the oldest lava flows in the Grand Canyon. The most recent lava flow in the Grand Canyon gives you the same rubidium strontium age of 1,143 million years. Why would that be the case?
Same source.
The same source. Remember? From the mantle below the Grand Canyon. And so the rubidium strontium is not the age of the rock, it's a record of the original chemistry of the source of the rock. Isn't that interesting? Well, I think we could have intermission, and you can go and get some hors d'oeuvres over there. I'll continue, I'll finish the story, and we'll go on this type of dating, and we'll go on talk about radiocarbon. So let's have a quick intermission. You got hors d'oeuvres there for us? Well, Steve, those hors d'oeuvres? Yes. Okay, guys, go and get some hors d'oeuvres. Give you a couple more examples before we talk about radiocarbon dating. And many granites, in fact most granites contain the mineral zircon, which is zirconium silicate. And the zirconium atom is the same size as the uranium atom and the same valence, +4. So uranium substitutes into the zirconium lattice, the zirconium silicate or zircon lattice. And zircons have become the gold standard for dating many rocks. And I'll come back to that in a minute with regards to the Topete sandstone. But I want to give you some examples of some granites that had the zircons dated using uranium lead, as well as that's the zircons from the granite, okay, and the zircons formed at the time the granites did, and the dating of the granite as a whole by another method. So, for example, in the Himalayas, one granite gave an age of 21 million years using potassium argon, but the zircon in the granite gave an age of 1,753 million years. That's 1.7 billion years. A granite in southeastern Australia, dated with rubidium strontium, gave an age of 426 million years, but the zircon grains in it gave an age of 3.5 billion years. And then I like this example. Another Himalayan granite gave an age of 20 million years using potassium argon. It contained zircon grains with an age of 1,483 million years. That's nearly 1.5 billion years for a 20 million year old granite. And in the same granite were monazite grains, which is a calcium phosphate rare earth mineral, and it was dated using uranium lead at minus 97 million years. At minus 97 million years.
Younger.
Yes. It hadn't formed yet.
Still waiting to form.
And those examples are in the literature. So you can see, as I said before, the rock dating methods have their problems, and even the secularists realise it, but of course they want to cherry pick their data. And I'll give you a supreme example is with regard to the Topete sandstone. One of the methodologies that are in vogue at the moment is to extract the zircon grains from a sedimentary rock like the Topete sandstone and look at the uranium lead dates of those zircon grains to determine where the grains came from. And so many of the grains in the Topete sandstone have a zircon age fingerprint, which is equivalent to the supposed ages of the granites and metamorphic rocks in the inner gorge, and that fits with the minerals that are in the Topetes. But what they also do is they look for the youngest ages of the zircon grains, because you would think, this countryside is eroding, and therefore the youngest zircon grains should be the age of the rock, because of the last grains deposited were from the most recent rocks. So by that method they determined that the Topete sandstone was 508 million years old. However, when you go to the supplementary data, that is the data that's the raw data that they didn't publish in the paper that was available if you went online and downloaded it, I went and looked at the actual raw data that they had, and there were a lot of grains that were younger than 508 million years old. There was one grain that was 407 million years old. How can there be a 407 million year old grain in a 508 million year rock? So, in other words, they cherry picked the data to get the age that they wanted for the Topete sandstone, and yet that was allowed to be published. So that's the state of play with these methodologies. It really is a numbers game to get what you want. And you think about it, they need the millions of years, because without the millions of years there's no time for evolution to occur. And what we've already discovered, of course, is with the remember we talked about the Cambrian explosion you get to the deplete sandstone and the layers above, and suddenly you have all these fossils, macroscopic fossils that we don't find them in the rocks below, like the docks here. There's the moon up there, the docks. And so the flood began and you got all these fossils. Well, there's nowhere in the supposed billions of years below that they've found evidence of the ancestors of those creatures that are buried in the Cambrian and above. And so even with the millions and billions of years, they just can't find the evidence for evolution. Well, what about radiocarbon dating? And you know, if you ever hear someone say to you that geologists use radiocarbon dating to date rocks, you know they haven't a clue what they're talking about. Okay? The methods they use, uranium has a half-life supposedly of 4.5 billion years. Potassium has a half-life of just over 1 billion years. Okay? Radiocarbon has a half-life that is half the amount will decay in that time period. It's a measure of the rate of decay. Radiocarbon has a half-life of 5,730 years. Only thousands of years. So in 5,007, if you start with a pound of radiocarbon, after 5,730 years, you'll only have half a pound left. Now, you think about it. Then after another 530 years, you'll only have a quarter of a pound. And it decays so quickly that if every atom of the Earth was radiocarbon, it would all be gone within 1 million years. And so that's why they don't use radiocarbon to date dinosaur fossils. Because after all, the dinosaur fossils are 66 plus million years old. And so they should be radiocarbon dead. That is, they should have no radiocarbon in them. Well, initially, that was a reasonable argument in the sense that the equipment they used initially, they had to shield the equipment with lead bricks because cosmic radiation would dwarf the signal they're getting from the radiocarbon, and so they had to develop a new technique. But let me back up a minute. Where does radiocarbon come from? It's not what the radiocarbon is in the plants around us. And you ate radiocarbon for dinner tonight, by the way, in case you didn't realise it. It comes actually, it's produced in the upper atmosphere. Cosmic radiation comes in from space. Fast-moving neutrons collide with nitrogen-15 atoms. 70% of the atmosphere is nitrogen, and converts that into carbon-14. And so carbon-14 is in the air we breathe. It's in the carbon dioxide the plants process with photosynthesis, and so it goes into the meat that we ate for dinner. And so every one of us has radiocarbon in our bodies. And when we eat more, it replaces what's decayed away. When we stop eating, of course, we don't take any more radiocarbon in. And so our bones will get less and less radiocarbon in the grave. So if we were to dig up your great-grandmother's bones and test them for radiocarbon, test your bones for radiocarbon, we know we can measure the difference. We know the rate of decay, so we figure out how long ago your grandmother died, your great-grandmother died. That's how the method works. Well, the newest technology, they actually can count radiocarbon atoms individually, but they ran into problems when they were trying to do some of the early work, because they could never get below 70,000 years. It was a practical limit that they could, and yet theoretically, with the equipment that they've been using, accelerator mass spectrometry, they should get back to 90 to 100,000 years. The quantities that would be left after that time should be detected. And so what they decided they'd do is they thought, well, maybe it's contamination in the laboratory with the techniques that we use to prepare the samples. So why don't we take material that shouldn't have radiocarbon in it, like dinosaur bones or coal or oil, and let's put that in the sample holder and test that. And lo and behold, every sample that was tested had radiocarbon in it. And so they thought, oh, there must be something wrong with our equipment and our chemical process. The interesting thing is the chemical process that they use to prepare samples is absolutely brutal. Hot acids followed by hot alkalis, followed by hot acids, and so it's chemically a brutal methodology. Do you want to say something, Joe?
I'd love to have a few words.
Yep, you go right ahead.
If I may interrupt.
That's okay.
Oh,
had
great
a
day
busy
today,
day.
you guys.
Yeah,
Yeah, that was awesome. Great hike. Woo! Yeah.
Yes.
All right. The moon, first quarter of the moon. That's pretty cool. Venus, if you walked out there, you'd be able to see Venus underneath the moon there, which is kind of cool. Yeah. How you guys doing?
Good.
Good? Yeah.
We're fed up.
Dinner was great, thank you.
Fed up.
Dinner was great.
Okay, great. Right on, you guys. Just a few words again to reiterate some of the things that I said yesterday about tomorrow. I think you said we're going to just pack up again. Is that right?
Yep.
Okay, good.
We'll pack up quickly.
I talked to Nate about our first possible stop down here, about 5 or 6 miles down the river, a place called Unkar Creek Delta. We may or may not stop there depending on the pull-in and what that is like. Usually we pull into a beach and walk up this trail underneath some trees, but I expect the pull-in to be right where the trees are. So, and they're the mesquites and the acacias. So if we can't step cleanly off the boat, I don't want to like put us into a bunch of thorns. Okay.
Yeah.
So, if we go, in either case, if we stop there or not, about 4 miles down the river from that, we hit Hance Rapid. So Hance is our first number 10 rapid, okay? So you guys probably know we rate the rapids on a 10-point scale down here, and it's roughly twice the equivalent of the 5-point scale that most of the rivers are used in the world. So meaning a 5 on another river is probably 10 here, that kind of comparison. The reason why we use the 10-point scale, number one, it started being developed down here previous to the 5-point scale. Actually, they use a 6-point scale now because a lot of the kayakers do that.
Yeah.
You know, they pitch themselves off of waterfalls. That's a class 6 right there. We're not doing anything like a 12 here or anything like that. We're not, yeah. So we've got 3 number 10s. That's Hance, Crystal, and Lava. And for both scales, the things that go into rating these rapids are the difficulty of the entry into the rapid, how you have to approach it, what kind of momentum you may have to have, the number of obstacles within the rapid, and number of moves that you have to make in order to avoid the obstacles. Most obstacles are walls or boulders, which form big holes. And of course, our motors stick down that far, so we have to literally be able to see that far underneath the water to know if there's a rock in there or not. So, the third thing to consider in rating a rapid is the consequences of failure of getting off of your line or staying on your line, failure to stay on the line. And, that could be getting stuck on a rock, flipping, that kind of stuff. But so that's what goes into rating these rapids. And it'll be interesting for both Johnny and I tomorrow because we know these rapids at a certain water level. but every rapid has its own characteristics at different water stages. So tomorrow will be a stage we've never seen before. So we're really excited about that. We will stop. We will stop at Hance Rapid and look at it, and depending on the conditions, more than likely we will ask you to just remain seated on the boat with your life jackets fastened. Johnny and I will go up there. I've invited Nate to come up as well, and maybe Walt, and we'll run up there, take a look at it, discuss it, compare it to the last time we ran it, which will be at a quarter of the amount of water that we'll see it tomorrow. So it'll be interesting for us, but we will be excited to run it. So if you could just remain seated and let us run up there and do it.
But watch out if he pulls out a beer before he goes to take through the rapid. We'll know we're in trouble.
Could be my last rapid. Yeah. But so then we'll probably take a pit stop somewhere in the morning, especially if we don't stop it on car. And then we are planning to stop at the boat beach between the Black Bridge and the Silver Bridge. And that's going to be a quick stop, okay? We intend to just run up and fill up our water jugs. There should be a spigot available to us to do that, so we don't have to filter and treat the water, and we'll have enough water for the remainder of the trip. Yes, ma'am.
Is that like a similar situation to where we left for this trip from, where it's a really long dock, or is there a chance we won't be able to land because of the increased water?
That's a really good question. There's no dock there.
It's the beach.
It is just a beach. I won't know until I get there, honestly. Yep, won't know until we get there whether we can pull over there or not at Boat Beach. Yeah. So I know at Hance there's different places to pull in there at different levels, and we need to go scout that, so we will find an appropriate place. But that is why I'm asking you guys to stay on the boats too. So yeah. So then we'll have lunch in there somewhere, and then go on down to Crystal Rapid. We'll scout that, and as always, folks, if you're really needing a pit stop, let us know, and we'll find an appropriate place to pull over. Okay. Yeah. Any questions about that? Pretty straightforward.
So we had one really juicy rapid, 2 days ago? It was on the left-hand side, big drop down in there. So how does what we're going to experience tomorrow compare to that one?
There is no comparison.
That rapid was tiny compared to what we're about to run tomorrow.
That was our biggest one.
We have not seen anything yet.
Yeah.
These are the
In
big
terms
rapids.
of whitewater.
Yeah.
Tomorrow we run what we call Adrenaline Alley, and it's the largest whitewater in North America. I expect it to be larger tomorrow than I've ever seen.
So, some years ago, I went through Hermit Rapid at 25,000 cubic feet per second, which is a little over half of what we're doing. And the crest to trough was 40 feet.
What?
40 feet, the difference between the crest and the height of the wave, the crest and the trough. 40 feet.
That's it?
We're not talking about centimeters.
That's it?
So one of these boats just disappeared.
Right on. Yes, Vivian.
What if we fall out during the rapids?
You won't fall out.
Don't fall
doesn't
out.
know.
Yeah.
Hang on.
You remember?
Won't know until we get
You
there.
remember what I said at the put in, right?
No.
About what to do. Number one, don't let go of the boat.
No eating Pringles during that one.
Yeah. No letting go of the boat.
Yeah.
Stay with the boat. If you do find yourself separate from the boat, we're going to try and get you back into the boat as soon as possible. Yeah.
Feet up.
Feet up.
Whitewater swimmer's position.
Downstream feet.
So feet downstream, head above the water. Remember to breathe
You know
when
that
your head
little
is above
pad
the water.
that's...
Make sure your life jacket's
back?
nice and tight.
That protects your head on the rocks if you're floating.
Oh, that's what it is.
But you want to go down
What time do we plan on meeting?
Same time.
It's always 8.
It might be a little earlier tomorrow than it was today. We do have a breakfast tomorrow of cold cereal, hot cereal, boiled eggs, and all the yogurt and fruit and other accoutrements. So
Will we be making sandwiches, or are we stopping
no,
somewhere?
we're planning on stopping. Yeah, we'll need a rest. Yeah, too. So Heather.
In the event that like we can't immediately get back into the boat, should we prioritize trying to get to shore or trying to get back to the boat? If we can do anything about it, because
Just look to the boatman. Look to the boatman. If you don't know what to do, just look to the boatman, and they'll guide you.
Yeah.
They did say if shore was close, just get out of the water.
Yeah.
Did that before.
I mean, definitely participate in your own
don't intend any
rescue.
yes.
Yeah. So if you're able to get out, you just
Get
get
out.
out. Yeah.
Vivian's got another question.
Yes.
So if this were to happen, what would happen if we were to like flip?
That's a great question. So there is a technique where if you're stuck underneath a boat that you need to just start going like this underneath the boat. I don't anticipate that happening. So if you are stuck underneath the boat,
And what does that do?
so
Get you
you'll-
out from underneath the
you will
boat.
be, if the boat's underneath and you're stuck underneath it, your life jacket will push you up into the boat.
Oh.
So what you need to do is just start doing this in one direction, and that keep going. And it may seem like
Yeah. Never
a long-
change direction.
Don't change direction. Just keep going like this,
Gradually get you out.
and then you'll pop out from underneath the boat. Yeah.
It's almost like you're
When
doing
you do
spider
one, you're
crawl
like
or something.
floating underneath,
Yeah.
floating.
At what point do you let go as you're flipping so you're free from the boat?
We're not going to flip.
Too much flip talk here.
Yeah, we're not going to.
No flips.
No more of that.
The pessimists aren't there, Joe?
All right. So, hey, thanks a lot for a great day.
We got faith in you guys.
Hey, I do wanna mention that where we had the line off of the boats is now underwater. So if you need to get to the boats to get us, if you walk toward the toilet and then walk up where my bow line is, you guys have seen the bow line that crosses. If you haven't been to the toilet yet, you'll see a bow line that crosses over where the toilet trail is. Go right up there, and then we'll be right down below that, okay? So that's probably easiest way to get to our boats if you need to meet us tonight, okay?
Or just find me. I'll be camping in the circle.
There you go. Nate will be right here.
We can go together.
Nate can come and get us if he needs, okay?
Thanks, guys.
Yeah!
Adrenaline Alley tomorrow.
Right on, you guys. Thanks, Andrew.
Quickly,
Because I can't see to the back of my tent.
okay, just quickly, with the radiocarbon. As I said,
Talk about heaven for a little while.
they've tested materials that span the age from the tapetes to the present, and they all have radiocarbon in them. That's fossils, fossil bones, limestones, marbles, oil, coal. So in a project that I was involved in, we got 10 samples of coal layers from around the US, from the Department of Energy Storage at Penn State University, and sent them for radiocarbon dating. And no matter the age of the coal, from 40 million years, the coal spanned from 40 million year age coal to over 300 million year coal from Pennsylvania. They all had the same radiocarbon age, approximately 48,500 years. Now, first of all, why would the coal, which is buried fossil vegetation, fossilized buried vegetation, why would it all have the same age? Radiocarbon age.
Happened at the same time.
They were buried at the same time. They were trees that were alive when the flood came. Why would they give a radiocarbon age of 48,500 years? Because the radiocarbon age is calculated based on the current rate of radiocarbon production in the atmosphere. What they don't take into account is that a stronger magnetic field in the past would reduce the amount of radiocarbon formed in the atmosphere. And we have good evidence, historically measured data, that the Earth's magnetic field is getting weaker. It was stronger, much stronger 200 years ago. The rate of decay is that it halves its energy every 1400 years. And so if you go back to the time of the flood, that means the radiocarbon production rate in the pre-flood world and up to the time of the flood was minuscule compared with now. So that would account for the inflated ages. We also decided to test diamonds for radiocarbon. And diamonds, being the hardest substance known, can't be contaminated externally or internally. And the diamonds, in fact, come from inside the Earth. The diamonds form in the Earth's mantle about 200 miles down. And I said the other night they're erupted explosively to the Earth's surface very rapidly. If they weren't erupted rapidly within a matter of hours from 200 miles down, they wouldn't remain diamonds, they would revert to graphite. And so that's why we know they had to come up very quickly. So these diamonds from southern Africa and from Africa gave ages around 60,000 years, radiocarbon ages. And when you do the math for correcting those, of course, with the inflated ages, that means they come down to being less than 10,000 real years old. So that means radiocarbon, if we know how to recalibrate it, and by the way, we're in the process, we've got some more diamond samples. We're at the moment negotiating with a laboratory to do more radiocarbon on diamonds, so stay tuned, there's more work coming on that. But think about it. If we could potentially recalibrate radiocarbon, if there were archaeological sites where we knew the exact biblical age and we radiocarbon material from that, then we could do a recalibration curve. Because the archaeologists know that beyond about 400 BC to 1000 BC, radiocarbon ages diverge from biblical ages. Radiocarbon becomes less reliable. So if we can recalibrate it from in known places, and so that there's discussion going on amongst a few of us with regard to that as well as a potential future research project. So radiocarbon is an interesting, another interesting side to the whole dating issue. It has its potential because it does give ages of thousands of years, and it does show that materials that are supposedly claimed to be millions and billions of years old can be shown to have young ages that fit the biblical timescale using radiocarbon. So we'll leave it there, and any questions we can take up subsequently. It's getting late, and I'm sure some of you want to crawl into bed.
Billions of years old, if not billions. Is it because of the half-life?
Yes, it's because of the half-life of those elements that are chosen. That's right, and the assumptions that are based, that they use to calculate the ages from the chemical analysis. Yes, it's because of the half-lives that they have.
Thank you.
Nate, did you want to? Was there anything you wanted to say or do?
No.
Pray for our boat.
Please don't have nightmares.
Yeah. It's gonna be fun tomorrow.
These guys are